Okay, so let's try another method of initial rates problem in order to determine the rate law and figure out the exponents and k and all that good stuff before we move on. So this is going to be a more realistic problem with normal numbers. I don't want to say uglier, but I mean it's not going to be, the numbers will not be as kind as they were in the last example. All right, so let's take a look at this problem. Here's what we got. The initial rates listed in the following table were measured in methanol solution for this reaction. C2H4Br2 minus plus 3 moles of iodide ion yields C2H4 plus 2Br minus plus I3 minus. All right, so that's your reaction. You've got 3 different experiments. Experiment 1, concentration of C2H4Br2 minus was 0.127 molar. Initial concentration of I minus was 0.102 molar. And then the initial reaction rate was 6.5 times 10 to the minus 5th molar per second. Experiment 2, you got 0.343 molar for the concentration of the carbon compound, 0.102 molar for concentration of I minus, and then the rate was 1.74 times 10 to the minus 4th. Okay. For experiment 3, the concentration of both of these have changed. The concentration of C2H4Br2 minus was 0.203 molar, so that went up. Concentration of I minus also went up. It's 0.125 molar. And then the rate also did something, 1.26 times 10 to the minus 4th molar per second. All right, so you got all that information. Here's what we're looking for. Part A, what is the rate law? Part B, what is the value of the rate constant in its units? Part C, what is the initial rate of formation of I3 minus when the concentrations of both reactants are 0.150 molar? Okay. Part D, what is the initial rate of loss of I minus when the concentration of both reactants are 0.150 molar? Okay. All right, so we've got a lot of stuff going on in this problem. This is a more realistic problem. This is definitely something that would be fair game on an exam, for sure. Okay, and if you take a look at those old exams that I posted, yes, this is pretty much it. You can definitely expect something like this in the homework and as well as on the exam. So what we're going to do is pretty much what we did in the last problem. We're going to compare experiments. Okay? Now, one thing right off the bat is if you look at experiment 1 and experiment 2, the concentration of I minus is the same. Okay? So that would be a nice one to use to figure out the concentration of C2H4Br2 minus. Okay? So we could use experiments 1 and 2 to help us figure out the exponent for this guy. Okay? And then we could use, for experiments 2 and 3, we could potentially use experiment 1 and compare it to experiment 3, or we could use experiment 2 and compare it to experiment 3. Either way is fine. Potentially, it could be better to use experiment 1 and experiment 3, but we're not necessarily committed. If you want to use experiment 2 and 3, that's fine. All right. So that's our first thing. We've got to get the rate law. We got to get the rate law, and we got to figure out what K is and the exponents. Okay, so let's try this out. So what we want to do is compare. Let's go after our first exponent. So we're going to compare the rate of experiment 2 to the rate of experiment 1. And so this is going to be equal to the rate constant K times the concentration of C2H4Br2 minus, okay, times the concentration, and that was raised to the m power, times the concentration of I minus raised to the n power. Okay. We're going to write the same thing for the rate law for experiment 1. rate law K times C2H4Br2 minus raised to the m power times I minus raised to the m power. And this is going to be equal to the rate of experiment 2 divided by the rate of experiment 1. Okay. All right. Now we know that the concentration of I is going to be the same thing for both of these experiments. Okay. So we've got the rate constant K. I'm going to write this out. We got the rate constant K times the concentration of C2H4Br2 minus at experiment 2. So that was 0.343 molar raised to the m power times the concentration of I minus, which is 0.102 molar raised to the n power. That's equal to the rate of that reaction was 1.74 times 10 to the minus fourth molar per second. Okay, let's write the rate law for experiment 1. The concentration for C2H4Br2 minus is 0.127 molar raised to the m power times the concentration of I minus, which is 0.102 molar raised to the m power, divided by that rate constant. That is equal to 6.45 times 10 to the minus fifth molar per second. All right. So what's nice is your K drops out. The I minus also drops out because that's the same. And now we got things a little bit trickier now, or a little bit simplified. It's going to get a little trickier in a minute. So to simplify, you have 0.343 molar divided by 0.127, and this is raised to the m power, is equal to 1.74 times 10 to the minus fourth divided by 6.45 times 10 to the minus fifth. Okay. All right, so now we got to do a little bit of math. We got to get rid, these numbers aren't going to be quite nice. So we're going to have to do some little bit of math work here. Let me get my calculator. Okay, so if we take 0.343 divided by 0.127, we get 2.7007. So I'm going to write 2.70 raised to the m power. All right. Now we got 1.74 raised to the minus fourth divided by 6.45 raised to the minus fifth. And that will give us about 2.697. So that's pretty close to 2.7. Cool. So what I'm going to do, let's try to solve for m. So to get m by itself, we're going to convert 2.7 raised to the m as a logarithm. So that would be m times the log of 2.70. And that's going to be equal to the log of 2.697. So m, if we divide the log of 2.70 from both sides, m would be equal to the log of 2.697 divided by the log of 2.7. That's going to be really, 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 really close to 1. We want the exponents to be whole numbers if we can help it, and there you go. The exponent for m is going to be 1. All right, so now we got to figure out the exponent for the next reaction. So let's compare the rate of experiment 3 divided by the rate of experiment 1. So let's try that. So we're going to rewrite that rate law. So it's going to be the rate constant times C2H4Br2 minus raised to the first times the concentration of I minus raised to the n power. We're still figuring that out. Okay, and we're going to write the same thing for the rate law for the first reaction. Okay. Now we're going to pop in our concentrations and what we know for experiment 3 versus experiment 1. So for experiment 3, we got the concentration of C2H4Br2 minus. That would be 0.203 molar raised to the first times the concentration of I minus, which is 0.125 molar raised to the n. And that rate was 1.26 times 10 to the minus fourth. Okay. For experiment 1, the concentration of C2H4Br2 minus, that was 0.127 molar raised to the first. And the concentration of I minus was 0.102 molar raised to the n. And so that concentration was that rate was 6.45 times 10 to the minus fifth molar per second. All right. So things don't quite cancel out for the ones, but we can get the K's out for sure. So that's good. We can get that out. Now, if we take 0.203 divided by 0.127, that should give us 1.5984. So if we round that up, that would be 1.60. Okay, so I'm gonna put that in concentration so that way in brackets, so that way we know we've taken care of that. Now, what we want to do is rewrite the expression so that way we got one fraction for the ends. So you got 0.125 divided by 0.102. So that should be 1.225, so 1.23 raised to the n power. That's going to be equal to, let's figure out the stuff on the right-hand side, 1.26 raised to the negative fourth divided by 6.45 raised to the minus fifth times 10 to the minus fifth. That should give us 1.95. So, all right, the numbers don't quite come out to be really nice numbers. We got to get n by itself. So the way we're going to do that is divide both sides by 1.60. That's going to be a start. All right, so there we go. So if we get, so we're going to have 1.23 raised to the n equal to 1.95 divided by 1.60. We should have 1.22. So we're close. We're super close. So number's probably going to be really close to 1. Let's check it out, though. Let's convert the exponent to a logarithm. So n times the log of 1.23 is going to be equal to the log of 1.22. So if we divide both sides by the log of 1.23, okay, n should be really close to 1. Okay, so now we've got our exponents. So based on what we know, the rate law would be this. The rate is equal to the rate constant K times concentration of C2H4Br2 minus raised to the first power times the concentration of I minus raised to the first power. All right, so we got that. Yay! Hard part's over. Now, second question. Going back up here, we got the rate law. Second question is this. What is the value of the rate constant and its units? All right, so what we're going to do is pick out one experiment and work with that. So let's go with experiment 1 only because that's our baseline. All right, so we've got our rate constant. We got our rate law. So let's pop in those values. So we've got K, which we're going to solve for, times the concentration of C2H4Br2 minus, which is going to be 0.127 molar, raised to the minus first power, times the concentration of I minus, which is going to be 0.102 molar, okay, raised to the first power, and that's going to be equal to our initial rate, 6.45 times 10 to the minus fifth molar per second. All right, so what we want to do is get K by itself. So I'm going to divide both sides by the concentrations. 0.127 molar to the raised to the first, 0.102 molar raised to the first. Okay, so that way they cancel out on the left-hand side. Right-hand side, we got 0.127 molar to the raised to the first times 0.102 molar raised to the first. Okay, so on the right-hand side, you've got a molar for the rate, and that's going to cancel out with one of the molars for the concentration. So you're going to have per second at the top and then mole on the bottom. So it's going to be, so the unit should be molar to the minus first because it's on the bottom, second to the minus first. So that should be the unit of K. All right. So if we take 6.45 times 10 to the minus fifth divided by the product of 1.27 raised to the first times 0.102 raised to the first, that should give us for K should be equal to 4.98 times 10 to the minus third, molar to the minus first, second to the minus first. And there you go. That's part B. What is the Ray constant? Okay. All right, we're doing pretty good now. We're cooking with gas. All right, so part C, the question that we had. What is the initial rate of formation of I3 minus when the concentrations of both reactants are 0.150 molar? So what I'm saying is that both of these are going to be that concentration. What's the initial rate of formation? Okay. All right. So what we're going to do is take our rate log. Rate is equal to K times the concentration of C2H4 Br2 minus raised to the first times the concentration of I minus raised to the first. The concentrations of both of these are going to be 0.150. So we're going to take our K, which that value was 4.98 times 10 to the minus third, molar to the minus first, second to the minus first, times the concentration of the first one, 0.150 molar, times the concentration of I minus, which is 0.150 molar as well. Okay. All right, so rate, the unit-wise, molar to the minus first should cancel out with one of our molars. So now the unit's going to be molar per second, so that's good. If you multiply these numbers together, you should get that the rate should be about 1.12 times 10 to the minus fourth molar per second. All right. Awesome. So that's going to be the initial rate of formation if the concentrations are both 0.150. All right, and then finally, the last question, and that was our part D question up here. What is the initial rate of loss of I minus when the concentrations of both reactants are 0.150? Well, wait. So the way that we just answered this was the rate of formation of I3 minus, okay, which is one of your products. So that should be a positive value. So if that's your initial rate of formation of a product, the initial rate of loss would actually be the negative of that. So that should be, for this answer for part D, that answer should be 1.12 times 10 to the minus fourth molar per second for the loss of I minus. Because this time it's negative because we're dealing with the reactants. And there you go. This is a really nice method of initial rates problem. This walks you through the steps of how do you solve for K, how do you solve for the exponents, and then how do you evaluate all that stuff that you just solved. So like I said, this is going to be something that you're going to be practicing on your homework, and this is definitely something you're going to be doing on your exam. Now, one thing that you may notice in the last video, that video was pretty close to about 35 minutes long, which is one of my longer videos. That being said, this is good. This is shaping up to be a long video as well, just for one problem. So here's the thing. Is there a faster way to do this? Yes. There's a much faster way to do this. But in order to use that way, we got to use some calculus. And that's what we're going to do in the next video. But if you had to do this experimentally, if you had to figure out the exponents in K and the rate experimentally, this is the way that you would do it.